You're fine. Yeah, you're fine. All right. Okay. Is it the last slide or not? Tell me. Yes.
Yes.
Yeah. Thank you. All right. So we talked about the modified sugars and modified sugars. They're important for the function of the macromolecules. And the last but not the least, there are many applications out there, but I'm giving only selective few. Most important for this class is the maintaining an appropriate glucose level. Who can tell me why you have to maintain the glucose level to keep you healthy? Can someone tell me? Why do you need the glucose level to check to keep you healthy? You guys are young. You don't have to worry about it. Once you become older, definitely it needs to be done. Who can tell me why the appropriate level of glucose is important for our health? Who can tell me? Anyone? Yes? Too much glucose can cause what? Diabetes. Diabetes, type 1, type 2, usually the type 2 is the one, big trouble. And 90% of the diabetes patients suffer from diabetes type 2, self-control. And type 1 is the insulin has problem. But the glucose level is the one causing it. Remember, glucose is important for our health. Whatever we eat, protein, the carbohydrates, those, and they basically generate the fuel, metabolic fuel, glucose, that goes inside the cell, degraded in the glycolytic pathway, to go to the TCA cycle, and ultimately electron transport chain to generate ATP. That's basically we need. Our brain needs about 70-75% of the ATP our body generates. So brain loves this glucose, but too much is bad. And because it can cause so many like diabetes and etc. It can go on from there. If the glucose level stays high, people can also die and go to the coma, right? So how do we measure the glucose level? The glucose level measures.
Caroline's
So
a
next question is how to determine glucose level in the blood. All right. So basically, a typical reaction is performed routinely, and that typical reaction is as follows. Okay. So that reaction is. Let me write down the glucose again. So glucose. This is the glucose structure. Come on. So glucose structure is C11O. Please write with me. You know the glucose structure, right? You already practiced the weekend. I'm positive. So that's our Fischer position formula. That's what the Fischer position formula is fine for the time being, huh? So carbon number 1, 2, 3, 4, 5, and the last one is CH2OH, right? So that's our glucose. Well, I did not put the hydroxyl group yet. I'm going to put it. So carbon number 1, carbon number 6. And we have a OH. Please write with me because you are practicing the structure. And that's a Fischer projection formula, right? Fischer projection formula, the line drawing. I'm not writing the Haworth projection formula for the time being. And because we are doing the certain reaction that takes place when we check the glucose level for any kind of individual. Normal person, diabetes person, or any kind of person, you take certain amount of blood and you perform this reaction. A drop of blood is good enough, right? So basically what happened is does the C1 oxidation. C1 oxidation. Please write with me. I'm writing, as you can see, very slow because of my cursor, and that's good for you. So C1 oxidation by the enzyme called glucose oxidase. GLC is a glucose, right? Abbreviation. And enzyme is called glucose oxidase. That's the enzyme the names comes from. So it oxidizes the glucose. C1 oxidation. Carbon number 1 is oxidized. And what the carbon number 1 has? Which group is this? Aldehyde. Aldehydes are oxidized to carboxylic acids. Everybody knows, right? Yes or no? Review. So basically what happened that aldehyde group is oxidized to carboxylic group. All right. Rest of the things remains the same. No change. All right. So this no change. All right. 1, 2, 3, 4, 5 and CH2OH. All right. So it's called C1 oxidation. What's the C1 oxidation means? The carbon number 1 aldehyde group is oxidized to gluconic acid. This is the name of the molecule is called gluconic acid. I'm going to write it down for you, and you must know the name of this acid and the conversion. You can say why. As you know the importance I told you earlier. We need to check the glucose level for everybody, huh? Well, once they get older, when young guys they're fine, they do plenty of exercise, burning lots of calories, but old guys are, as you know. So now the byproduct for this reaction is this molecule. So you have the H2O2. Who can tell me what's the name of this molecule, H2O2? I'm going to write the name of this molecule, okay? It's called gluconic acid. Gluconic, NiC, huh? Gluconic acid. So gluconic acid, you have a gluconic acid, all right? Gluconic acid, ACID, huh? ACID. So gluconic acid plus hydrogen H2O2. Who can tell me what's the name of the H2O2? No?
Hydrogen peroxide.
Thank you very much. Yes, it is. So this hydrogen peroxide, as you can see, one molecule of glucose, take one molecule of gluconic acid and one molecule of H2O2. So therefore, it's a 1-to-1 ratio. So as many H2O2 you can quantify this one. That many glucose molecules are there in the blood. How do you quantify? You add a molecule, it looks like this. It's called orthotoluidine. Let me give you the structure first. And this is structure. It's a 6-member ring. Please write down 6-member ring, huh? And it is a benzene ring circle. It is NH2 amino group right there, NH2, and there is a methyl group there, CH3. So it's a 6-member ring, and this circle represents you have a triple bond. All right, double bond, 1, 2, and 3. So it's a circle. So it's called orthotoluidine. The name of the molecule is called orthotoluidine. Toluidine. All right. Toluidine. All right. So everybody okay? Orthotoluidine is the name of the molecule. Orthotoluidine. That's a molecule. And this molecule is a colorless. No color. All right. So it's a colorless molecule. So basically, you take this molecule, it's a colorless molecule. Colorless, huh? Colorless. And then add an enzyme. We need an enzyme, of course, there to perform this reaction. It's called peroxidase. Oxidase again. So it's a peroxidase. All right, peroxidase. So peroxidase is a peroxidase. Orthotoluidine and peroxidase will react to the H2O2 and will make the compound looks like this. Please write down the structure. As I said, it will be very important. It will be in the test, of course, no doubt about it. And what we'll have, the molecule looks like this. CH3 remains as it is. All right, and this molecule, the NH2 group, converted to keto group, C double bond O. Rest of the things are the same. Rest of the events no change. And this is the color. It gives the color. So what basically happens, if you quantify the color, just give the color. And once you quantify this color, basically it gives you as how many molecules of H2O2, and that corresponds to how many molecules of glucose. So this is so that's basically the color is quantified. All right, it is quantified. As you quantify, and it gives a number, right? It will give a number, and that number is usually I'm going to give a normal person. Usually, if it comes to let's say 70, which is very low number, but it's okay nowadays. Diabetes Association basically they give this number 70 to 90 milligrams per deciliter of blood. DL, deciliter of blood. So if you have this number 70 to 90 milligrams per deciliter of blood, that basically person is normal. All right, it's a normal person, normal individual. Maybe all of you write this, right? It's a normal. If it goes, usually it used to be 90 to 110. But once again, it depends on the association. They basically lower the number, and it's good for that, good for the health. But it is very difficult to maintain, of course. Maybe you guys can if you burn a lot of do the exercise. But 130 and above is considered as pre-diabetes, right? 130 milligrams per deciliter of blood above is diabetes, pre-diabetes. And then above, if you go 180 and above, is a diabetes. And if someone has or gets to 600 and above and stays for a while, that person can go to the coma. Very dangerous disease, right? Very dangerous condition for a patient. All right. So that's the importance of this. How to determine the glucose level in the blood. You take a tiny amount of blood, a drop of blood, put in the strip. As you know that those are routine kits are available from the companies selling it. And nowadays, some companies are even selling with strips. You just put in your body, any part of your body. Sweat comes from your body, and that's good enough. That will sense it, will give the glucose level. Some companies are developing. You take a small amount of tears. You have to cry then, huh? You have to take a tears from your eyes and put in the strip, get the glucose level. So you can say why many people don't like the sticking to the finger with a drop of blood, right? Once again, so this is the reaction routinely used and all those enzymes and everything are in the strip. So basically, you take a drop of blood, and within a few seconds, in fact, it takes 15 to 20 seconds or so, maybe less sometimes, and you get the number. All right. Now, any questions on this? You must know this. It will be the test. Any questions? Yes? All right. No question asked. Right? Okay. All right. So then let's go to the various types of saccharides. Saccharides are sugar, right? So most saccharides are classified based on the number of units present. They are called monosaccharides. Monosaccharides include glucose, galactose, mannose, and fructose. Glucose, galactose, mannose. Yes. 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 I cannot hear you. I cannot hear you. The mic is not working properly, I guess. All right. So glucose, galactose, mannose, they are the aldoses, and fructose is 1-ketose. And these are our monosaccharides. These are our metabolic fuels, as I told you earlier, right? Disaccharides includes but not limited to when two monosaccharides are linked together. Two monosaccharides linked together, it's called disaccharide. Di means two, right? And examples are lactose. Who can tell me where do you find the lactose? Anyone? Where can you find the lactose? Come on.
And milk.
Milk. Yeah, thank you very much. Milk. Any kind of milk. Cow milk, goat milk, mother's milk, any kind of milk has plenty of lactose. Plenty of lactose. And how do you find the sucrose? How do you get the sucrose? Yeah. How do you get the sucrose? It's a table sugar. That's a table sugar. That's a sugar that we routinely use. That's for buy from the grocery. Table sugar. And how do you find the maltose? It's from the malt. Malt is a type of grain. And cellulose is basically a combination of cellulose is a combination of glucose. It is a precursor of cellulose. Cellulose. They are disaccharides. So galactose, the chemical form of galactose looks like this. So chemical form of galactose, you have a lactose. Chemical form of the lactose is you have a galactose linked with beta, you remember the beta, right? Beta NO1, beta 1 carbon of galactose linked with 4 carbon of glucose, GLC. And you can put the parenthesis. So that's the chemical formula or chemical linkage. The galactose is the combination of lactose is the combination of galactose and glucose linked via beta 1 carbon of galactose and 4 carbon of glucose. That's our lactose. Chemical linkage. Yeah.
When you say 4 carbon glucose, what do you mean?
A carbon has how many carbon?
What?
Glucose has how many carbon?
6, right?
Yeah. The fourth carbon linked with a galactose.
Okay, so
Yeah.
you're saying that only 4 of the carbons in glucose linked to galactose. That's what you mean?
Not the 4 carbon, fourth pH. Fourth carbon is linked to the galactose. Fourth carbon. First carbon, second carbon, third carbon, and the fourth pH, fourth carbon. So fourth carbon of glucose linked with first carbon, carbon number 1 of galactose via beta linkage. Sucrose, the chemical form is glucose, GLC, linked with fructose via alpha carbon 1 of glucose and 2 carbon number 2, second carbon of fructose. So glucose linked to the fructose via carbon number 1 of glucose and carbon number 2 of fructose. That's a linkage. The linkage between the two. And given by glucose and fructose, we have all alpha and beta position, alpha and beta anomers. Usually the alpha anomer linked to the fructose.
Okay, I have a question.
Yeah.
Okay, so for the lactose, so I'm trying to get this straight. So the lactose, so what the beta 1 is for lactose is bonded to the carbon 1 of galactose. Is that what you're saying?
So lactose is the 2 disaccharides, the 2 monosaccharides. One is a galactose, and one is a glucose. Yes or no?
Can you say that again? I didn't get it.
Lactose disaccharide.
Okay.
Yes? It has a 2 monosaccharide. One is a galactose and one is a glucose. Yes?
Okay, so,
And they're linked here, carbon number 1 of galactose and carbon number 4 of glucose. They're linked together.
Okay.
Okay?
Thank you.
Same thing, sucrose. Sucrose, carbon number 1, linked to it, carbon number 2 of fructose. That's the sucrose. What is the maltose? The malt. We are factoring all those things they use this grain, plenty of it. It is glucose, GLC, alpha, carbon number 1 of glucose, GLC, and carbon number 4 of another GLC, another glucose. Once you put them together, you get the maltose. Likewise, cellulose, you get the GLC, right? That's the GLC, the chemical linkage of cellulose, GLC, beta 1,4 GLC. Who can tell me what's the difference between the maltose and cellulose? What's the difference in maltose and cellulose? What is the difference, chemical difference between maltose and cellulose?
One has beta and one has alpha.
So basically, maltose linked to the 2 glucose via alpha. Yes or no? Yes?
Yes.
And cellulose linked to the 2 glucose via beta anomer. Remember the anomer, alpha anomer, beta anomer, right? Yeah. So now, if you continue this one, add n number of glucose, n number of GLC, n could be millions, then you end up with a polymer. That name of the polymer, you end up with a polymer. So basically what happened, GLC, 1,4 GLC, next one is alpha 1,4 GLC, next one is alpha 1,4 GLC, and you can go n times. N is usually millions. N is greater than equal 10 to the power 6. molecules of glucose linked via alpha 1, 4 linkage. And you end up with a polymer, a polysaccharide. You end up with a polysaccharide. The polysaccharides are coming from the disaccharides, in fact. Yes? For example, maltose can link the alpha 1,4 linkage and continue doing it as many as you want. That can get a polysaccharide. So as many millions of molecules. That one, the example of that polysaccharide is glycogen. It's glycogen or starch for the plant. Glycogen for the animal. You can tell me what's the glycogen? What's the glycogen? Have you ever heard the glycogen? Have you ever heard the glycogen? Yes? Have you ever heard the glycogen? Huh? It is a storage food. It is in our liver. 10% of our liver mass is the glycogen. Animal. And starch and plant for the same thing. Is a plant is also it's another name for starch for same linkage, same kind of polysaccharides. The polysaccharides of glucose, alpha 1,4 glucose, in millions of molecules, they make a storage food in form of glycogen and starch. Glycogen and starch. Now, you can do the same thing here. You can add plus n number of GLC. Same here. N number of glucose molecule. And this n is greater than equal 10 to the power 9 billion molecules, billions of glucose molecules added together. So basically same linkage, right? GLC beta 1,4 GLC, next one beta 1,4 GLC, beta 1,4 GLC, and go on and on and on and on. Up to how many? Billions of molecules. And that results into a polysaccharides. Again, it's a polysaccharides, right? That is also goes to the polysaccharides. And the name of the polysaccharides is the cellulose. What do you see the cellulose? You can tell me, how do you see the cellulose? What do you see the cellulose? Anyone? What do you see the cellulose? Yeah? The plants, the plant, the root, stems, bark of the tree, all those things consist of cellulose. Cellulose, right? You're writing in a piece of paper, and that piece of paper contains cellulose, polysaccharides. So you got the monosaccharides, disaccharides, so these maltose can also be used in the food. Why food? Because this is storage food, glycogen, right? You can degrade it into glucose, you can have a food. Same maltose is the disaccharide can also make a polysaccharides, the storage food, glycogen or starch. Starch in the plants, glycogen in animals. Cellulose, linkage is beta 1,4 and it makes the cellulose. So our body, animal system and the plants also, they can break this alpha 1,4 linkage to make glucose. Humans cannot break the beta linkage because you do not have the enzyme necessary to break this part. Only some 4-footed animals can break it. They have some enzyme, some strain of bacteria that secretes that enzyme to leave or to break this beta 1,4 linkage to make glucose. So they can use the cellulose, the grass, leaves, and that's basically those 4-footed animals eat, right? And that's basically they make the cellulose. They can digest it. They have enzyme. You don't have it. You do not have it. So sometimes if you hear that your goat ate your homework, right? It's a typical excuse. And indeed, goat has the enzyme that can degrade the paper, piece of paper, cellulose. We don't have it. We cannot degrade it. All right. So that's basically monosaccharides, disaccharides. Some disaccharides make the polysaccharides, and I give you some example. Cellulose is involved in structural and protection of the plants. As you probably know, the stem, the roots, etc., all those are structural and protection for the plants. Cellulose. All right? Yes, Marcia. Yes, Marcia.
Can you explain the difference between the oligosaccharides and then the polysaccharides? I don't understand what the difference is between the two.
So, oligosaccharides, I'm coming. I didn't go through oligosaccharides. It's hanging there. Did you get the polysaccharides?
Yeah, I got the polysaccharides.
Good enough. Monosaccharide just hanging there. Monosaccharides, disaccharides, and polysaccharides. You got it, right? Yes? The next one is, this one is oligosaccharides. So what's the difference? What is oligosaccharides? If you have 3 or more monosaccharides or modified monosaccharides linked together, that's oligosaccharides. And usually it never goes more than 20. Whenever we say more monosaccharide, 2, 3 or more, usually it never goes up to 20. Not only that, sometimes, some cases, most cases, it's about within 3 to 4. 3 to 4, some cases 5 at the most. Saccharides, monosaccharides together make the oligosaccharides. Is it okay now? What's the oligosaccharides versus polysaccharides? Say? Yes?
Yes, thank you.
You're welcome. Polysaccharides are millions of molecules, maybe billions, depending on the organism. Oligosaccharides are only 3 or more, at the most 4 or 5. So what's the application of those oligosaccharides? They are mostly antibiotics. As we take. We have many antibiotics, many different classes, and those antibiotics, I'm giving you the structure only, just look at it, and you can write the names, of course. Streptomycin, definitely you have heard of it. It's a broad range of antibiotics. It kills different strains of bacteria, gram-positive and gram-negative combined. Erythromycin is derived from azithromycin. Azithromycin is universal. It's used all over the world. Antibiotics to kill bacteria. Almost it's universal. And not only this, these antibiotics, azithromycin, nowadays have been used to slow the growth of the COVID-19. Although COVID-19 is a virus, but some viruses need bacteria to grow, and that azithromycin kills the bacteria, those kind of bacteria. So azithromycin and erythromycin is derived from azithromycin, in fact. Or I could say azithromycin is derived from the erythromycin. They are all broad range of antibiotics. They kill a series of bacteria, gram-positive and gram-negative combined. So what's the difference? Yes, Sophia? What's up?
Do we need to know the structure of these?
Oh, I don't think so. Do you think so? Do you think so that you should know? I don't think so. No, not at this stage. No. Not only that, if you ask any doctor, if you go to, no offense to anybody, no doctors, if you go, I don't think so. No one can drive the structure. But maybe when they learn in the medical school, definitely they learn those structures, but they forgot right away. You cannot draw this structure. All right, it is only for the bookkeeping, but that's okay. So just see the structure. What you see the structure in the streptomycin, that's a sugar. These are modifications. Another sugar, modifications. Another sugar, modifications. So they are modified sugars linked, as you can see, linked to the carbon number 1, and all linked together, right? So this is the streptomycin. Erythromycin also have a sugar, modified sugar, and linked to the 14-member ring. There's a 14-member ring there, right here. That ring has a keto group. There's so many things up there. And this is being modified to add the NCH3 group. So it is a 15-member ring now. It's called azithromycin. It's a azolite derivatives of the antibiotics, and it is widely used all over the world to kill bacteria, along with the antiviral agents, viral compound or viral drugs. Okay, this is being used routinely for many countries, many places, to stop the COVID-19. By the way. All right, so these are the antibiotics derived from the they're in the class of oligosaccharides. Oligosaccharides are basically a class of antibiotics. Many of the antibiotics are in this class of oligosaccharides. Just write down the names. That's good enough for the timing. Okay. All right. Next gives you the practice homework assignments. And do you have any question? By the way, you can ask any questions if you have. Otherwise, we're done for the first part, and your test. I'll explain more details on the Friday. What will be the test? Definitely up to this point, and read those the practice homework assignments. Everything will be in the test. All right. up to this point. Whatever we're talking today will be in the test. All right. So what are stereoisomers? You already know. A non-superimposable mirror images of the molecules. All right. Epimers. Who can tell me what's the epimers? And can you give an example of epimers? What's the epimers? Anyone? Let's see who is reading for the test.
Would it be D-mannose and D-glucose, which are two epimers, and then, yeah. I think there's
Absolutely right. And glucose and galactose are the 4 epimers. Yeah, absolutely. Who can tell me what's the anomers? Anomers. What's the anomers? The same carbon, same molecule. Alpha and beta configurations of the glucose, right? Alpha D glucose, beta D glucose, alpha D fructose, beta D fructose, they're all basically are the anomers. All right, very good. The next one is the, oh come on, give me a second please, oh my cursor. What are the D and L configurations of a chiral center? You know the chiral center, right? The carbon is surrounded by 4 different groups of atoms at the chiral center. If you pass a plain closed light, you may deflect on the right hand side. That's a vector rotatory. D. If the light is deflected to the left counterclockwise or left hand side, it's L configuration. All sugars in our body, all natural sugars have D. All natural sugars have a D configuration. There are some exceptions, of course, but don't worry about exception. 99%, 95%, more than 99% cases, all sugars, naturally occurring sugars have D configurations. What are the precursor of aldoses and ketoses? You already know. Right? Desaldehyde and dihydroxyacetone is a ketoses. Give the structures and you already have it. Explain the test that is used to measure the glucose level in the blood. Sit down. I'm not going to say it again because I just said it a few minutes ago. How many chiral centers are present in glucose and fructose in their Fischer projection formulas and Howard projection formulas? You already know that, right? And you must know. So the structures. In other words, practice the structure for the test. What are the basic differences between sugars present in RNA, D-ribose, DNA, deoxyribose? What's the difference between those two? Carbon number 2 configurations. What are the applications of monosaccharides? Metabolic fuels. Disaccharides, some of them metabolic fuels, and some of them can form polysaccharides. Some of them will generate polysaccharides, and some of them are also food particles, right? For metabolic fuel, like a sucrose, galactose, maltose in some extent too. But once they become polysaccharides, it could also be a food as well, storage food in fact. And oligosaccharides, antibiotics, polysaccharides are used as storage food, glycogen starch, example. Cellulose is the protection and structural already. Any questions before I go to the next step? Any questions before I go to the next step? Yes? Any questions before I go to the next step? All right. Seems like no questions. So now, remember what we talked about earlier. So this is the slide, for example, right here. So the glucose levels, D-glucose, galactose, mannose, all those things are metabolic fuels. So what do they do? And that is the next one. That is our next step, right? So metabolic degradation of sugars. Sugars, specifically the monosaccharides. If you have a disaccharide in our diet, for example, milk, lactose, plenty of lactose, right? If we have some table sugar, and in the form of cake or something like that, right? It goes to an intestine, goes to a stomach. Intestine has some enzyme. Those enzymes, for example, lactase, TAC, lactase, will degrade the lactose into galactose and glucose. Sucrase will be degraded by the glucose and fructose. So all those disaccharides that we take in our diet, in the intestine we have some enzyme, will degrade into monosaccharides. Those monosaccharides ultimately will go to the glycolysis. Glycolysis is the first step of the degradation of sugars. How does it work? So we take first, once the glucose, we're starting from the glucose. Glucose is converted to glucose GLC 6-phosphate 6P with the help of enzyme called hexokinase. Hexokinase. All right. I'll give you some enzymes. I'll not give you all of them. You're going to be able to remember probably, but that's okay. You don't have to. If you already know, that's great. So it takes the ATP. The glucose with the hexokinase, ATP, make the glucose 6-phosphate. What the glucose 6-phosphate means? Who can tell me? Remember, glucose has 6 carbon, right? 1, 2, 3, 4, 5, 6. And 6 carbon is CH2OH. That OH, H is replaced by the phosphate group. So it is a CH2O PO3 2 minus. That's a glucose 6-phosphate. The glucose with enzyme called hexokinase, it is with the form of ATP. ATP gives the phosphate. It's converted to glucose 6-phosphate. That's the first step of the glycolysis. Glucose 6-phosphate are converted to fructose 6-phosphate. All right, fructose 6-phosphate with the help of enzyme called isomerase. Isomerase is the enzyme. If you remember, fine. I'm going to give you the name. Isomerase. Right. So isomerase, its name is glucose 6-phosphate isomerase. It is converted to, remember, right? Isomers are converting cis trans isomerase. Isomerase converted to fructose 6-phosphate. Fructose 6-phosphate, the enzyme called fructokinase, it is converted to fructose bisphosphate 1,6 BP. It is also known as FBP. F for fructose, B for bis means 2, phosphate means phosphate. Right? So fructose 6-phosphate with the help of kinase again, another kinase. I'm just writing in kinase general name. It's called PFK, phosphofructokinase. Kinase, ATP. It is converted to fructose for F. Instead of writing all those things in a word, right? F fructose 1,6 bisphosphate. B means bis means di 2. FBP. So carbon number 6 is already phosphorated here. Carbon number 1 is now phosphorated. So you have a CH2O PO3 2 minus in one side. Another side is CH2O PO3 2 minus. Fructose 1,6 bisphosphate. FBP. Now FBP with the help of enzyme called aldolase. Aldolase is an enzyme. What it does, it will cut into 2 pieces. All right, it will cut into 2 pieces. One is called dihydroxyacetone phosphate, dihydroxyacetone phosphate. Another one is called glyceraldehyde, G3P. So G3P stands for glyceraldehyde. G3P stands for glyceraldehyde 3-phosphate dihydroxyacetone phosphate. The help of enzyme called aldolase. Remember, this is a carbon number 6, right? This is a carbon number 6. Fructose has carbon number 6. Fructose bisphosphate has carbon number 6. With the help of aldolase, it becomes a C3 and C3. So it is split into half and half. 2 C3 molecules. It cuts exactly in the middle of the fructose 1,6 bisphosphate to make the dihydroxyacetone phosphate and glyceraldehyde 3-phosphate. All right. So that carbon-carbon bond is clipped by this enzyme, and the energy associated, the potential energy associated with the carbon-carbon bond, is split into two molecules, and that energy will be multiplied the next few steps. Then dihydroxyacetone phosphate. Yes, Jenny.
I'm sorry, really quick. What's the word that you wrote under phase 1? Right above one of the arrows?
Right here.
Yeah.
ISO MERASE, isomerase.
Okay, thank you.
You're welcome. Now, dihydroxyacetone phosphate is further converted to disulfide phosphate by the enzyme called triose phosphate. Triose isomerase. Triose isomerase. Alright? Triose isomerase. Convert the dihydroxyacetone phosphate to two molecules of disulfide 3 phosphate. Initially, you had one molecule of dihydroxyacetone phosphate, another molecule of disulfide 3 phosphate, G3P. Dihydroxyacetone phosphate, with the help of enzyme triose isomerase, is converted to glycerolide 3 phosphate. So basically, one molecule of glucose generates two molecules of glycerolide 3 phosphate. This is the end of phase 1 glycolysis. This is our end of phase 1 glycolysis. Tell me, anyone has any questions? Phase 1. All right. Phase 1 glycolysis. Anyone has a question about phase 1 glycolysis? Phase 1.
Can you say the word again for the GP? So I know the last word is phosphate, but I do not know about G.
This one.
No, it says G3P.
A G3P.
Yes. What did that stand for again?
Glyceraldehyde 3 phosphate.
Okay, thank you.
Okay. All right, that's a phase 1 glycolysis. So in a phase 1 glycolysis, one molecule of glucose is converted to two molecules of glyceraldehyde 3 phosphate, G3P. Everyone okay? Yes?
What is the enzyme that converts the DHAP to the G3P?
It's a triose. TRIOSE, triose isomerase. ISOMERASE, isomerase. Yeah? Okay.
Professor,
Yeah, I know the time is up, right? Yeah.
what's the name?
Say it again.
What's the name of the above the arrows that converts FBP and what's that?
It's the
The
aldolase. Aldolase.
Aldolase? Okay.
Yeah. ALDOLASE. Aldolase. Yeah. Yes. Any other questions? I'm going to stop with the phase 1 glycolysis. We'll convert the phase 2 glycolysis after the test. Oh my goodness. After the third test. All right. So I'll see you on Friday. And Friday I'll go through details of the exam. If you have any question, please ask. My officer is still there. I'll have officer on Wednesday as well, although it is holiday. But if you are free, if you have questions, read this weekend. Read this time, anything you can. I'm just telling you again and again.